This meeting is now being recorded.
Hello, I'm Sharon Kirkpatrick from the U.S. National Cancer Institute. Welcome to a third webinar in the Measurement Error webinar series. In Webinar 2, Dr. Kevin Dodd provided an overview of methods of estimating usual intake distributions for non-episodically consumed foods. Today, we'll continue with the theme of estimating usual intake distributions, but this time with a focus on episodically consumed foods with Dr. Janet Tews. A few quick notes before we get started with the presentation. The webinar is being recorded so that we can make it available on our website. All phone lines have been muted and will remain so throughout the webinar. There will be a question and answer period following the presentation. If you'd like to submit a question, you can do so using the chat feature at the left of your screen. A reminder that various resources, including the slides from this session and the glossary of key terms and notation, are available on the webinar series website. The URL is available in the note box at the top left of your screen. Now let's move on to today's presentation. We're fortunate to have Dr. Janet Tews as a member of the Surveillance Measurement Error Working Group at the National Cancer Institute and as a presenter in this series. Dr. Tews is an associate professor in the Department of Biostatistical Sciences, Division of Public Health Sciences at Wake Forest School of Medicine. She has expertise in longitudinal data analysis and nonlinear mixed effect models, with specific applications to diet and physical activity assessment. Her work to develop a statistical model for repeated measures data with excess zeros provided a foundation for the development of the National Cancer Institute, or NCI, method. As I mentioned earlier, in today's presentation, Dr. Tews will discuss the estimation of usual intake distributions for episodically consumed dietary components. In contrast to Webinar 2, in which Dr. Dodd provided an overview of different methods of estimating usual intake distributions, Dr. Tews will focus specifically on the application of the NCI method. Dr. Tews?
Thank you, Sharon. I'm excited to have a chance to talk today about one of my favorite topics. I'd like to begin by acknowledging the multidisciplinary team of presenters and collaborators from various institutions who have contributed to the development of the NCI method and to this webinar series. This series is dedicated to the memory of Dr. Arthur Shatzkin. This seems especially appropriate for my webinar today, as it was a talk I heard by Dr. Shatzkin about dietary measurement error 10 years ago that inspired me to start working in this field. It is my hope that, in some small way, this webinar series inspires you to begin or continue research related to dietary measurement error and its implications. This slide probably looks familiar if you've watched the last two webinars. As has been mentioned, the webinar series will cover two main areas of interest: describing usual intake distributions and estimating diet-health relationships. In the first case, we are interested in distributions and associated statistics such as means, percentiles, and proportions above or below a threshold, such as a nutrient requirement or food group recommendation. In studying diet-health relationships, we're interested in regression coefficients that describe the relationship between a dietary exposure and an outcome, such as an odds ratio, a relative risk, or a slope. In this webinar, similar to the last webinar, I will be focusing on the first area, that of describing the usual intake of distributions, and future webinars will address diet-health relationships. We are interested in estimating distributions of usual intake of foods and nutrients in many arenas. This includes informing research, establishing population norms, and guiding public policy. In the first webinar, Dr. Sharon Kirkpatrick introduced the concept that the regularity with which a dietary component is consumed among a population of interest is a key concept in modeling usual intake. We can think about two different types of dietary components: nutrients in foods that are consumed nearly daily by nearly all persons, such as vitamin C, total grains, and total fruits and vegetables, and those that are consumed episodically by most persons, such as nutrients that are concentrated in a few foods like vitamin A, and food groups that are not commonly consumed every day by many individuals, such as whole grains and dark green vegetables. Now, unlike the last webinar, we will focus today on episodically consumed dietary components, which pose some unique challenges to statistical methods. So the learning objectives of the webinar today are to define the key concepts of food consumption related to usual intake estimation, to identify the challenges for estimating usual intake, specifically for episodically consumed dietary constituents, and to explain the statistical modeling approaches that are used to overcome these challenges. Finally, I will apply the MCI macros to an example of estimating the distribution of an episodically consumed dietary constituent to illustrate their use. These are the key concepts that guide the estimation of usual intake for episodically consumed dietary components. First, as I've already alluded to, consumption patterns vary across dietary constituents. Second, usual intake is comprised of the product of the probability of consumption and the consumption day amount. In addition, dietary data are often skewed and, as was discussed in the first webinar, current dietary assessment measures are prone to error. I will address each of these concepts in more detail. Dietary constituents are simply the components of a diet, which may be described as individual foods, food groups, or components of foods such as macronutrients and micronutrients. In general, foods and many food groups are episodically consumed. That is, they are consumed by many individuals on a less than daily basis. In contrast, many nutrients are consumed daily by most persons in the population. Of course, there are exceptions to these categorizations. For example, some food groups such as total grains and fruits and vegetables are consumed on a daily basis by most individuals, and some nutrients such as vitamin A are episodically consumed. Here is an example of a food group that is consumed daily by most persons, total grains. This plot is a histogram of total grain intake in ounce equivalents reported by men on one 24-hour recall from the Eating in America's table study. You can see here that all of the men reported some grain consumption, even if it was a small amount. We also see a common characteristic of dietary intake data here, a distribution that is skewed to the right, with one man consuming over 41 ounce equivalents of total grains per day. In contrast, here is the consumption of an episodically consumed food group for the same group of men on the same day of recall, whole grains. We see a large spike at 0, which I have indicated with a white diagonally striped column, indicating that 36% of the men reported no intake of whole grains for the day of 24-hour recall. Among those men who did report whole grain consumption, we also see a skewed distribution, with one man consuming over 11 ounce equivalents on the recall day. This spike at 0, followed by the ramp, is a very common pattern for episodically consumed dietary constituents and other variables that exhibit clumping at 0 as well. With dietary surveillance, as I mentioned previously, interest is on usual intake, which is a measure of long-run or habitual intake for an individual. Interest is generally on estimating this long-term intake because nutrients can be stored in the body and intakes vary from day to day. Therefore, it is usually unnecessary and impractical to achieve nutrient and food intake recommendations every day. There are some notable exceptions to this statement, however. For example, for alcohol consumption, there may be interest in intake for a given day to define activities such as binge drinking, but we make this general assumption for almost all dietary recommendations. For describing the usual intake of episodically consumed dietary components, it is helpful to break down usual intake into two components. it can be seen that usual intake is the product of the probability of consumption and the consumption day amount. When a dietary component is consumed every day, like total grains, the probability to consume is 1 or nearly 1, and therefore it is only necessary to model the consumption day amount. However, when foods are not consumed daily, it is useful to separate probability and consumption day amount. This plot illustrates usual intake of a food over time for a hypothetical person over 10 days. The horizontal axis represents time in days, and the vertical axis represents food intake in cups. The dots represent intake on 1 day, and the dashed line represents usual intake, which you can see from the plot is about a half a cup. You can see that person A did not consume any of the food on the 4th or the 7th day, consuming the food on only 80% of the days, so the probability of consumption is 80%. If we ignore the 2 days where the food was not consumed, we can see by the green solid line that the average consumption day amount is approximately 2/3 of a cup. Finally, we can calculate the usual intake by multiplying 80% by 2/3 of a cup, giving us the usual intake of a half a cup. It's also very important to note that we often see correlation between probability and amount. This is illustrated in this plot, which is a 24-hour recall whole grain intake data for men from the Eating at America's Table study, which collected 4 24-hour recalls. Along the vertical axis is 24-hour recall reported ounce equivalent consumption, and along the horizontal axis is the percent of the 4 24-hour recalls that have reported intake. As you can see from the dots, there is a positive correlation between the proportion of days that whole grains are consumed and the amount eaten on the consumption occasion. This is not surprising. It just means that men who eat whole grains more frequently tend to eat more of them, perhaps because they like them. We see this for about 80% of foods. There are a few food groups that don't exhibit this correlation, such as dark green vegetables. People tend to consume the same serving size no matter how often they eat it. As was discussed in Webinar 2, and as we saw for both total and whole grains, dietary intake data are often skewed. This is an example of folate intake, showing that some values go up to 1,500 micrograms per day. These right-skewed data are common in studies of dietary intake, even for episodically consumed foods and nutrients. And, as was discussed in detail in Webinar 1, current dietary assessment measures are prone to error. In the next few slides, I will briefly summarize some of the slides from Webinar 1 that describe measurement error in FFQs and 24-hour recalls. There are roughly 5 sources of within-person error: day-to-day variation and random error in reporting, which are both random and cannot be distinguished, so we simply refer to them as random within-person error. This variation affects the variance, but not the mean of the distribution. In addition, additive error, intake-related bias, and person-specific bias are systematic sources of error and lead to biases in estimation. Recall from Webinar 1 that the systematic error can shift both the mean and variance of the distribution of usual intake. The findings of the Observing Protein and Energy Nutrition study, which Sharon reviewed in Webinar 1, suggest that 24-hour recalls have larger within-person random error than the FFQ, but smaller systematic error. The random error in the 24-hour recall is driven by day-to-day variation in intake and other random errors that affect reporting from day to day. The error in the FFQ, on the other hand, is driven by inaccuracies associated with the task of recalling long-term intake, as well as features of the instrument, such as the finite food list and the relative lack of detail about the foods consumed. So what instrument do we choose? Well, the 24-hour recall is the instrument most commonly used in dietary surveillance and is the instrument I will refer to in the remainder of the webinar. I've added 2 dots to this earlier plot, representing that often only 2 days of 24-hour recall are available, and that these can be reported with random error. This is an important assumption that the 24-hour recall is prone to random but not systematic error. With only 2 days of 24-hour recall, we are able to estimate usual intake by accounting for this random within-person error by using statistical methods. This assumption of unbiasedness is a working assumption for the 24-hour recall. As Sharon discussed in Webinar 1, the critical assumption of unbiasedness does not hold in practice for the 2 biomarkers studied in the open study, energy and protein. However, in the open study, the 24-hour recall was subject to less systematic bias than the FFQ. Unfortunately, we don't have other recovery biomarkers to know how well it works for the other dietary components. So essentially, the 24-hour recall is one of the best dietary assessment tools we have, and we proceed under the working assumption that 24-hour recalls are unbiased for usual intake. So now that we've reviewed some key concepts, let's move on to challenges to assessing usual intake for episodically consumed foods and nutrients. In the previous few slides and in the earlier webinars, we have seen that dietary data are prone to measurement error and tend to be skewed. Therefore, our models must accommodate these challenges. In addition, with episodically consumed dietary constituents, we have to model consumption patterns. That is, we need to model both parts of usual intake, probability of consumption and the consumption day amount, as well as the correlation exhibited by these 2 components of usual intake. Finally, there is often interest in incorporating covariates, and there may be interest in incorporating different sets of covariates into the model for probability and amount. So I'm going to briefly discuss each of these challenges in a bit more detail in this section, and then I'll get into the details of the statistical modeling in the next section. Let's discuss the impact of random error on the estimation of intake distributions, where typically we rely on 24-hour recall data. Here we are looking at a hypothetical distribution of intake. The widest distribution, shown by the greenish line, shows that intake based on a single day has the widest distribution. The gray line shows intake based on 2 days, and the solid blue line shows the actual usual intake. So we see the distribution of intake based on 1 day is wider and flatter compared to the usual intake distribution. The graph also shows that averaging over 2 days may help somewhat to alleviate the effects of within-person error, but is certainly not sufficient to account for that error. An important implication here is that if we do not account for measurement error, it will result in overestimates of inadequate or excess intake. This is illustrated by the vertical lavender line on the left side of the slide. If this represented a hypothetical threshold, we can see that both the 1 day of recall and the 2-day mean overestimate the proportion of the population in the tail. This suggests that simple analysis methods based on averaging are not generally satisfactory. A number of methods have been proposed to estimate usual intake distributions for episodically consumed foods using short-term instruments like the 24-hour recall, including those on this slide, which I have listed in chronological order. The general approach used by these methods is to separate the within and between person variation and to remove the within person variation using statistical modeling. This is done using a normality assumption because the normal distribution has a number of nice properties, one of which is that it's defined by 2 parameters, the mean and a constant variance, as was discussed by Dr. Kevin Dodd in Webinar 2. And, as we've said, this modeling makes an important assumption that the 24-hour recall is only subject to random error. So, to explain this graphically, our goal is to go from the wider distribution on the left to the narrow one on the right, which does not exhibit within-person variation. You may have noticed on the previous slide the nice bell-shaped curve of the distribution, because when we separate between from within-person variation, it's very helpful to assume that the data are normally distributed. We'd really like our raw data to look like this, as we've seen in the previous slides. But unfortunately, they usually look like this. There is a way to deal with skewness, however. You may remember from a statistics class that when data are skewed to the right, that we apply a power transformation to pull them in. This is exactly what we do in the modeling. We start with the 24-hour recall data in the original scale and apply this type of transformation that is similar to a square root or a log transformation to obtain a normal distribution. Now, the within-person variation still exists in the transformed scale, but it is now possible to apply a statistical model to remove its effect and get the more narrow distribution that exhibits only between-person variation. However, because we used a transformation, but we would like usual intake on the original scale, we have to make one last step to translate back to the original scale. All of the methods I mentioned use this general framework for transformation, although the types of transformations vary. So when we do these back transformations, our goal is to estimate a quantile on the original scale that corresponds to one in the normal distribution. That is, we want the median and other quantiles on the transformed scale to be mapped back to the quantiles on the original scale. We also want the mean on the original scale to match the mean on the transformed scale. However, as Kevin discussed in Webinar 2, taking the mean of transformed data is not the same as transforming the mean when the transformation is nonlinear. So we have to find some way of approximating the estimated quantile in the back transformation step. As Kevin mentioned, the quantile is an integral that can be approximated in a couple of ways. One way is to use an approximation such as the Taylor series approximation, which he discussed. Another way is numerical integration using quadrature formulas or Monte Carlo integration. The basic idea behind quadrature is to approximate the integral by breaking it into smaller pieces and to sum the value of the integrand over a series of points using specific weighting coefficients for each point. The trapezoidal rule is a simple case of this method with which you may be familiar. In contrast to quadrature, Monte Carlo integration uses random points to approximate the integral. Whatever method we use, it is an important step to ensure that the data are back transformed to the original scale, so that the mean on the original scale is equivalent to the mean after the back transformation. Previously, I mentioned that it is helpful to divide usual intake into two parts, probability of consumption and the consumption day amount. All of the methods that I listed estimate these two parts of usual intake, although they differ in the way in which this is done. In the NCI method, in order to model episodically consumed foods, we fit a two-part model, where the first part is a mixed model logistic regression, and the second part is a mixed model linear regression on a transformed scale. I use the term here mixed model to describe a model that has both fixed effects, as in usual regression, and random or person-specific effects. The mix of the fixed and random effects gives us the name mixed model. These person-specific or random effects are latent. That is, we can't directly measure them. They are constant for an individual, and they capture how an individual's value deviates from the average after adjusting for covariates if we have them in the model. We can think of them as a person's tendency to consume a certain food or nutrient, and the variability of the person's specific effect, therefore, captures the variability of the population. We incorporate person-specific effects in both parts of the model, although each part of the model has a different effect. As you may recall, most foods exhibit correlation between the probability of consumption and the consumption day amount. Therefore, it is important that a statistical method for estimating usual intake be able to accommodate this correlation. In the NCI method, this is done by allowing the person-specific effects to be correlated. With correlated effects, we must model probability and amount simultaneously. In addition, the two parts of the model may share the same covariates, although the covariates may be different if desired, or there may be no covariates. This three-dimensional plot shows the joint distribution of probability amount with the positive correlations we often see. Along the axis to the right side of the graph, we have the consumption day amount. On the axis to the left side, we see the consumption probability. The vertical axis represents the distribution density. Notice that the lowest points of the graph for probability and amount are at the point closest to the bottom, so that as the probability increases, consumption day amount also increases. So lower probability is associated with lower amounts, and the higher probability is associated with the higher amounts. This is the space that we are modeling with the correlated two-part model. In addition, there is often interest in incorporating covariates into statistical modeling. For example, we may want to correct for individual-specific effects that affect true intake, such as gender, age, or race and ethnicity. One reason we may want to include these types of covariates is to make different estimates of the distribution of intake for different subpopulations in an efficient manner. We may also be interested in adjusting for time-dependent covariates that affect true intake on certain days, such as season or weekend versus weekday. Finally, we may want to adjust for nuisance variables that are related to reporting error. These can include interview sequence effects, where the first interview day usually reports higher intake, and mode effects, such as in-person versus telephone administration. So I've already briefly introduced the NCI method, and now I will discuss it in more detail in this section. This is an overview of the NCI method, which was developed by me and other members of the Measurement Error Surveillance Working Group. Part 1 is a mixed model logistic regression to model probability that may incorporate covariates. Part 2 is a mixed model linear regression that models amount on a transform scale to account for skewness. This model can incorporate covariates and also separates within and between person random error to account for measurement error. Finally, the two parts of the models are linked by allowing the person-specific random effects to be correlated. This models the correlation we often see between probability and amount. The two parts of the model may also be linked by sharing covariates. I'm going to describe the model in statistical notation briefly before turning to an example. First, we let Tij be the true intake for a person I on day j. We also let P sub I be the true probability to consume. That is, the probability that the true intake is greater than 0 given the person I. Next, we let AI be the true average consumption day amount. That is, the true average intake given that the individual consumed on that day. Finally, we can see that the true usual intake is the product of the probability and the amount. Now, unfortunately, we don't have truth, but we have the 24-hour recall reported intake Rij instead. We make some important assumptions in the model about Rij. First, we assume that if someone ate a food, that he or she reported it on the 24-hour recall, and conversely, if a food is reported on the 24-hour recall, then it was consumed. This means that the probability P sub I is the same as the probability that the 24-hour recall is greater than 0. Second, we assume that the 24-hour recall is unbiased for the consumption day amount. This is another way of saying that the 24-hour recall only has random error. Although there may be some noise with the 24-hour recall estimates, we assume that, on average, they estimate the true consumption day amount. Putting these two assumptions together, we assume that the 24-hour recall is unbiased for the true usual intake T sub I. As I mentioned before, the probability to consume is modeled using a mixed model logistic regression, and here we use H to indicate the logistic function. Because it's a mixed model, it has both fixed effects corresponding to the covariates X1I and random effects U1I. So U1I is a person-specific random effect that allows a particular person's value to differ from that defined by the covariates, and we assume these random effects are normally distributed. Recall the assumptions that we made about the 24-hour recall earlier. We have to add one more assumption to this list that is related to the amount part of the model. Specifically, we assume that on the transform scale, the amount has additive and independent measurement error. On the transform scale, we model the consumption day amount as a mixed model with fixed effects corresponding to the covariates X2I, the random effect U2I, and the within-person random error EIJ. Both the random effects and the within-person errors are assumed to be normally distributed, additive, and independent. Finally, we assume the two random effects, U1I and U2I, have a bivariate normal distribution. That is, they are correlated, indicated here by the parameter rho. The model is fit by maximizing the likelihood using a quasi-Newton optimization of a log likelihood approximated by adaptive Gaussian quadrature. As I mentioned earlier, quadrature is a method of numerically estimating an integral. This is implemented in a SAS macro that calls proc NL mixed. The macro may be downloaded at the website address given here. The mixed-strand macro works by fitting a fixed effects model and two uncorrelated logistic and linear models for probability and amount to obtain starting estimates of the model parameters. It then fits the two models simultaneously with the shared correlation parameter. SAS is required to run this macro. I've described the NCI method for fitting the model, but fitting the model is really just the first step of the NCI method. To estimate the distribution, we use a Monte Carlo approach to generate the bivariate distribution of random effects using the parameters that were estimated in the modeling. As I mentioned earlier, Monte Carlo is a numeric approach for approximating integrals like quadrature is. It uses random points to estimate the distribution, however, so you can think of it being a way of simulating the distribution based on the model parameters. Most of the time, we use 100 realizations of the random effects for each person in the data set. We then combine the estimated random effects with the empirical distribution of fixed effects that come from the data. Finally, we back-transform the estimates and multiply by the estimated probability to get an estimate of usual intake on the transform scale. Originally, in the NCI method, we used a Taylor series approximation to back-transform the data, as Kevin described in Webinar 2. This method works very well in many cases. However, when there is a large amount of within-person variation compared to between-person variation, this method does not work as well as the 9-point quadrature method the ISU method uses. For this reason, we now recommend the quadrature method for general use. Finally, percentiles may be estimated from the sample quantiles from the representative sample of the 100 times n back-transform values, and the sample fraction that fall below a given cutoff comprise the estimates of the proportion of the population with usual intake above or below that cutoff. The Monte Carlo distribution method is implemented in the SAS macro distrib, which may be found at the same website as the Mixtran macro. Currently, the distrib macro uses the Taylor series approximation. We're in the process of updating the macros and incorporating the 9-point approximation. So now let's turn to an example. This example is from the Eating at America's Table study, or EATS. This study was conducted on men and women ages 20 to 70 years old. Approximately 1,600 subjects were recruited from a nationally representative sample. 965 respondents completed 4 24-hour recalls, 1 in each season, and an FFQ, NCI's Diet History Questionnaire, about the previous year. The example I'm going to talk about today is for estimating whole grain intake for men in EATS. You've seen this plot before. Recall that over a third of the men in EATS did not consume any whole grains on the first 24-hour recall, and on the consumption days, the data were skewed. Furthermore, the correlation between the probability and amount for whole grains was about 0.3. This indicates that the men who consumed whole grains more frequently consumed more of them. So I wanted to show you how I fit these data in SAS. The first line here shows how I load the macro into SAS. In particular, I have stored the Mixtran macro in a folder called C/NHANES/macros. You would just want to make sure you update this to wherever you have the macro stored on your computer. This %include statement will read all of the macro code into SAS so that it is ready to execute the macro. Next, I'm going to go through each statement I put into the macro call, which is indicated by the statement %mixtran. A SAS macro is a useful technique for rerunning a block of code when you want to change just a few variables. In these statements, I am defining the macro variables, so the macro will replace the generic macro variable name, such as data, with the real name of the data set I'm using, which I've called min. Next, the response variable is defined as R_G_WHL_TOT, which is the variable that describes the total intake of whole grains on the 24-hour recall for a particular day. I'll stop here and note that it's important that the data be arranged in one row per day and sorted by ID and day. In this case, I have 4 recall days, so I have 4 observations or 4 lines of data for each man. The food type variable is a little different from the previous ones I've defined because it doesn't correspond to a variable in the data set. Instead, it is used to label the data sets. I have decided to call my food type GWHLM, but I could have chosen another name. In the next statement, I've defined the variable that identifies the subject or participant, which in this case is the variable NID. Then I define the variable that identifies the day of the 24-hour recall from 1 to 4. It is called intake N. If I wanted to incorporate covariates into the probability part of the model, I could put them in here with spaces in between the variables. However, I've decided to fit the distribution here with no covariates, so I just leave it blank. I've also left the amount part blank as well. The outline variable defines the name of the library where the output data sets will be stored. In this case, I've already defined a permanent SAS directory or library called webinar using a live name statement. If I wanted to create temporary data sets, I could use the word work here. Because this is an episodically consumed food, model type = core is specified. This fits the 2-part model with correlated random effects. There are also options to fit an uncorrelated model or an amount-only model for daily consumed constituents. The macro variable title saves one line for a title supplied by the user. Other numbers of lines can be specified. The print level is 2, which prints the output from the NL mix runs and the summary. So the mixtran macro saves the parameter estimates and the predicted values in 2 data sets. They have the general form given here, and the specific file produced from my call is given below. The term vcontrol is an optional macro parameter that may be specified in the model when you have difficulty getting the model to converge and want to put in starting values from a previous run. It is appended at the end of the file name if used. If you would like more information on the macros, a user guide is included on the website. When print level is set to 2, the mixtran macro will produce 3 sets of NL mix output for the correlated model. It also prints out a summary of the uncorrelated and correlated model runs, including the parameter estimates and the AIC and -2 log likelihood for the models. For the correlated model, it compares the -2 log likelihood to the uncorrelated model and calculates the p-value associated with the comparison. If the test is significant, it indicates there is correlation between probability and amount, and the correlated random effects model should be used. Here is the output summary table from the uncorrelated model. The uncorrelated model is equivalent to modeling the probability of consumption and the consumption day amount separately, but it only works if there is no correlation between these 2 parts of the model. It's important to make sure you check the message that the model, or in this case the 2 models, have converged. The parameters that are marked with P correspond to the probability part of the model, and the parameters marked with A correspond to the amount part of the model. Lambda is the Box-Cox, or power transformation parameter. In the next table, the AIC for each part of the model is given, along with the sum and the corresponding values for the -2 log likelihood. The correlated model summary output is similar to the previous page. I'm just going to point out the additional test here for the comparison to the uncorrelated model, which in this case is highly significant, indicating that there is a positive correlation between the probability of whole grain consumption and the consumption day amount. So let's turn to the distrib macro, which is used to estimate the distribution of usual intake after we estimate the model from the mixtran macro. It uses the input from the mixtran macro. As before, I've used the %include statement to load the distrib macro into SAS. Next, I call the macro with the %distrib statement. So remember how I stated the Monte Carlo procedure uses random numbers? All this statement does is set the seed in SAS to generate the random numbers. 0 selects the date and time as the random seed. The NCSIM_MC macro variable sets the number of Monte Carlo simulations per person in the data set. In this case, I've used 100. As before, the model type is core. I'm now inputting the data sets from the previous run. First the predicted values, and then the parameter values. Also, as in the mixtran run, the library I'm saving to is called Webinar. The cut point statement allows me to calculate the estimated % of the population below these particular cut points I've specified, here from 0.1 to 4 ounce equivalents of whole grains. In the next macro variable, I simply put in how many cut points there are. In this case, there are 13. The subject variable is NID. I save a line for the title, and I've decided to call my food or dietary constituent G whole M. This is used to name the output data set given below. And this is the output that prints from the distrib macro. It prints a few selected percentiles and the sample size and mean from the estimated distribution, as well as all 13 cut point probabilities. And here is a partial printout of the descript_G_M_ data set that is output by the macro just using a proc print. It gives the mean, the sample size, and all of the percentiles from 0 to 100, along with the 13 cut point probabilities. These are smooth histograms showing the approximate distribution of whole grains per min and eats. Ounce equivalents of intake are shown on the horizontal axis, and the percent of participants in the group are given on the vertical axis. These are kernel smooth estimates. You can see here a big spike indicating that 8% of the men did not consume whole grains on any of the 4 days in eats. In contrast, we see a smaller percentage in the tail for the NCI method. However, the smooth histogram is a little difficult to interpret due to the bumpiness from the data and the semi-continuous nature of the 4 mean data. So I am also showing the cumulative distribution function for men. From this, we can estimate the proportion of men consuming more than a certain number of ounce equivalents per day. You can see here that the 4-day mean estimates a higher proportion of men that have intake under about 1 ounce equivalent in the left side of the plot. The 4-day mean also diverges from the NCI method in the other tail of the distribution. This indicates that a higher percentage of men are below recommended intakes using the NCI method as compared to the 4-day mean. And we can see what these estimated percentages are in this table for both men and women. So for example, for men, the 4-day mean method estimates that about 21% of men are consuming less than 1/3 ounce equivalents of whole grains, but the NCI method estimates this number is about 10%. In the upper tail, the 4-day mean estimates that about 14% of men eat more than 3 ounce equivalents per day, but the NCI method estimates this number is only 11%. So it's interesting to compare the NCI method to the 4-day mean for the eats data. However, we were interested in seeing how our method would compare to truth. So in order to do this, we simulated data. Data were simulated based on the eats data set, and the data were simulated to have the 24-hour recall consumption pattern that was seen for women in eats. Like men in eats, the probability and amount were correlated for whole grain intake for women. So we generated 300 data sets of size 2,000 individuals each with 365 simulated recalls for each person. The mean of the 365 days was considered to be true. And then we then fit the model on 2 of the recall days 300 times and took the average and compared it to truth from all 600,000 data points and to using a 2-day mean. Here are the estimated distribution curves from the smooth histograms. In these curves, the red line, which is dashed, represents truth. The gray dashed line, which is very similar to the red line, is the NCI method, and the 2-day mean is shown in black. You can see the NCI method is very close to truth, and the 2-day mean has a big spike of 0 and a long tail. This plot shows that the NCI method, as is shown by the gray dashed line, consistently had low bias. This is indicated by it being close to the 0 line, and it's especially true compared to the 2-day mean. This plot shows the cumulative distribution function, with the dashed red line again representing truth. The NCI method, which is shown by the gray dashed line, and the 2-day mean shown by the black line, cross around the mean, indicating that if you just want to estimate mean intake, both of these methods are okay, but you will see very large differences in the tails. And here are the percent above cutoffs for the simulations. In this case, we see that the NCI method is closer to truth than the 2-day mean, especially in the tails. For example, the table shows that for the simulated data, only 1.2% of the simulated population consume more than 3 ounce equivalents of whole grains per day, but the 2-day mean estimated the value to be 6.1%. The NCI method was close to truth with a value of 1.1%. So to summarize the simulation results for whole grains, the NCI method is less biased for estimating usual intake than the 2-day mean. When estimating the percent above or below a certain number of servings at the mean, both of the methods do well. But above or below the mean, the NCI method is closer to truth, and the simple mean tends to overestimate the proportion who consume in each of the tails of the distribution. So in conclusion, the 2-part model I've presented here is appropriate for the estimation of the usual intake for episodically consumed foods and other dietary constituents. The NCI method in particular accounts for the challenges of episodically consumed constituents, including measurement error, skewness, separation of probability and amount, as well as their correlation, and is able to incorporate covariates into modeling.
Thank you, Dr. Chews. We'll now move into the question and answer period.
Okay, thanks, Janet, for the excellent presentation. We do have some questions for you. One is, how do you decide if a dietary component is episodically consumed or not?
That's a good question. There's no hard and fast rule, but generally what we see is that if you see more than 5 to 10% zero intake, it's generally beneficial to use a 2-part model.
Great, thank you. What about dietary components that are episodically consumed by some subgroups but not others? And the example given is milk that might be episodic among non-Hispanic blacks but not non-Hispanic whites. If you want a population estimate, how do you handle that?
Well, there's a couple of ways you can do it. You can fit for example, in this case, we might use age and we might also use race, ethnicity as variables in the modeling as covariates for both the probability and the amount. And we can estimate different estimates for the subpopulations. Now, I didn't really have time to go into it today in detail, but you have to be really careful and that you are appropriately modeling the variance components and when you do this. And there are ways of checking this statistically. So it would be possible to do it within the modeling framework. It would also be possible to just do a stratified analysis and to fit, if you're really concerned about making estimates for one subgroup, you might want to consider doing a stratified analysis for episodically consumed components for that subgroup and fit perhaps just an amount model for a subgroup that was not episodically consumed.
Thank you. The next question, does the NCI method provide confidence intervals for the percentiles of the usual intake distribution?
You can get standard errors of the estimates by using bootstrap methods. We have a paper that illustrates this when you have nutrients or daily consumed dietary constituents. You can use the bootstrap method to get estimates. We haven't actually implemented it in the macros yet, however.
Okay. How would you apply these statistical methods to 3-day food records?
With 3-day food records, they're generally treated as each food record, each 3 days food record sort of treated as an eating occasion and as a short-term instrument itself. So you would need to have repeats of the 3-day food records, probably, a week or so apart on at least a subset of the population in order to be able to separate out the between and within person error. And then you could proceed in a similar manner to what I described for 24-hour recalls.
Great. Would you recommend using the NCI method when you have data from 2 or fewer 24-hour recalls?
You can use the NCI method if you have data on 2 24-hour recalls on at least a subset of the population. You can't use it if you only have 1 recall. You really need to have 2 on at least some people to be able to figure out what proportion of the variability is within subjects and which is between subjects. And if you just have 1 recall, the sources of error are put together.
Okay, this question's a little bit related. In practice, if you have only 2 24-hour recalls per person, are there problems getting the model to converge?
No, not really. I mean, there can be problems getting the model to converge. I won't lie about that. It's probably, modeling is really more of an art than a science, but it's probably more limited by the number of people than the number of recalls generally when we have convergence problems. Of course, having more recalls is helpful. Having more people, of course, is helpful. And then it can also depend on the proportion of people who have zeros and who are included in the in estimating the probability. And then it can also depend on having enough people to make sure that at least some of them consume the food or nutrient on the 2 days in order to be able to fit the model. I'll just comment that with convergence problems in general, I've generally found the best thing to do is to try to update the starting values that are used in the nonlinear mixed effects model in procanal mixed, and we do have that function that I briefly touched on to be able to do that in the macro.
Okay, this is a follow-up question to an earlier one about food records. Is there any benefit to collecting a 3-day food record as opposed to 2 or more recalls?
I don't know that I'm the best person to answer that question. I don't know. I mean, you really would have to think about the different sources of error that you might see. Of course, you would have a somewhat longer period than the 24-hour recall, which could give you some benefit. However, some studies have shown that food records can be more reactive, that when people think about what they're eating, they might go, oh my God, I ate that much, that many Hershey's Kisses, and then they may kind of modify what they eat. So there can be some concern that food records might not reflect usual intake as well as a 24-hour recall, especially if people don't know when the 24-hour recall is coming. But I'm a statistician. I'm not an expert I'm not a nutritionist, and so I won't comment on those aspects much more. Statistically, I don't think there's really much difference in the modeling, as long as we don't have, the only kind of caveat to that is it's possible to have some autocorrelation perhaps when, let's say, you eat a food on one day and then you eat leftovers the next day. And currently we don't model autocorrelation or serial correlation in this modeling approach.
Okay, another related question. Do you know if there's been a study comparing distributions based on recalls as compared to 3-day or multiple-day diet records?
No, I'm not aware of any study that's done that.
NCI method been validated against known biomarkers such as total energy expenditure or urinary nutrient excretion, which it might be thinking about urinary nitrogen there.
We haven't done this directly for energy or for protein intake. Larry Friedman does have a paper that incorporates biomarkers and estimating distributions of intake, but we haven't written any specific manuscripts to do this with the NCI method explicitly.
Okay, so changing topics now. What do you do if the density of the 2-day means shows 2 peaks?
Well, I guess I didn't really get into this either, but we do make the assumption in this that we don't have 2 peaks, that we just have the one spike at 0, and that the data are able to be transformed to a normality. And so if you can't do that, if it's not possible to transform your data to normality, then the method's not going to work perfectly in the way it's supposed to. I haven't really done any simulations to be able to tell you how much off it may be, but that certainly is a good point that you should look at your data. I always suggest to people that they should look at their data graphically, and that's part of the reason I show those histograms and things is because I think that's always an important first step, to look at your data and make sure that it can be appropriately transformed.
Great, thanks. Speaking of 0 intakes, what if reporting of 0 intake is biased? For example, if overweight individuals over-report 0 intake of high-calorie foods?
Well, that would be a systematic error, and so that would probably be a kind of person-specific bias. And the general impact of person-specific bias is to not impact the mean of the distribution, but to impact the variability. And so it could lead to biased estimates of the distribution of usual intake. Lots of people have tried to look at this question, including me, trying to figure out if there are certain factors that may impact underreporting, or trying to predict underreporting, and it turns out it's very difficult to do. I did some analyses of the open data and found that I could only explain about 10% of the error in the FFQ and 25% of the error in the recalls by looking at things like BMI, fear of negative evaluation, social desirability, dieting, things like that. And so, at this point, there's just not really good ways of correcting for those factors. And so that's why we just have this working assumption that the 24-hour recall is only subject to random error.
Okay, so following up on an earlier question, what proportion of the sample do you need to have a second recall on to properly estimate episodic food intake distribution?
It really can vary a lot by the food. As I said, you want to make sure that you have a sufficient number of people who would have the food intake on both days. And so, you want to have at least 50 to 100 people who would have the food intake on both days. And so you kind of need to take into account what the probability of consumption on any given day is, and and then use that to calculate how many people you would need to have the repeat days. And of course, you also then would need to think about whether you wanted to make estimates for certain subpopulations and things like that. So it depends a lot. If you wanted to do something like soy, which very episodically consumed, you would need a lot more people than if you wanted to look at something like fruit consumption or even whole grains that are not quite as episodically consumed.
So sticking with that topic of episodic consumption levels and zeros, there's a question about how to handle vegetarians, presuming that they're episodic, I guess, in a number of different food components.
Okay. Well, I suppose you'd want to be, I guess it would depend on whether, your entire population were vegetarians or you somehow wanted to model them within your population. You could certainly use an indicator as to whether or not someone was a vegetarian as a covariate in your modeling and make subgroup estimates. And this kind of relates back to the earlier question about, different groups having different types of patterns. You just really probably would you just want to really think about it and be careful in the modeling to either, you can try doing it as a subgroup analysis within the model, or you could try, you may just want to stratify for that group.
Great. Can you speak to the use of an FFQ in estimation of intake distributions for episodically consumed components?
Yeah, that's a good question. I'm glad that someone asked that. An FFQ, those of you who have heard the earlier talks on the NCI method and maybe read the papers may have noticed that originally, and I think this is still in many people's minds, that the NCI method was developed as a way of augmenting 24-hour recall data with the FFQ. And the reason that I didn't emphasize the FFQ as a covariate today, and you notice I didn't include it as a covariate in my example, is that it turns out that when you're really interested in the distribution of usual intake, the FFQ is not that helpful. It's just because we're interested in describing the distribution of intake, and so it's not going to make that much difference whether the FFQ is included as a covariate or not for surveillance. Now, in later webinars, when we start to talk about diet-health relationships, the presenters will talk about how the FFQ can be incorporated, and it turns out that with predicting individual intake, it can be really helpful to include the FFQ as a covariate in the modeling. And so I've really de-emphasized the FFQ because it's not always available on everyone who has a 24-hour recall. For example, in NHANES, it's not available on everyone. So you can really limit your sample if you require an FFQ, and you may also, limit people by literacy or income or some things that might be related to the FFQ non-response, and it's just not that helpful. I actually have estimates for the whole grains that show using the FFQ versus not using the FFQ, and they're almost identical. And so you saw in the example that the whole grains was very close to truth in our simulations, and adding the FFQ into that didn't change that relationship at all. Just it barely made a difference.
Okay. How would you apply the NCI method to multiply imputed data?
That's a good question. That's something that I don't have a good answer for, because it's something that's actually come up with some of these, trying to do some of these methods statistically, and it seems like there's some extensions of the NCI method that we've been trying to do some multiple imputation, and it's been difficult. So it's not something that I've tried yet, so I don't really want to speak to that.
Okay, this question I think is in follow-up to the walkthrough that you did of the macros and the output. The question is about how you would present the findings. So when using the NCI method for episodic components, is there a recommendation in terms of the statistics that you would report in a journal article?
Oh, okay. Well, gosh, I think it just depends, again, on what you're trying to show. A lot of times what we've done, and what I did today, was I reported the percent that are below cutoff. And I think the reason for that is just because that's what's often recommended in, let's say, dietary guidelines or some other types of dietary recommendations or dietary goals. And so we often use those. But on other applications of this that I've done, sometimes we just are interested in reporting the median, perhaps with a standard error of the estimate, or the 25th or 75th percentile to show an estimation of spread. So I think it just depends on, what your goal is in using this method.
Thank you. Can the methodology be adapted for use in analysis of institutional menus when only 2 days from a cycle of menus can be analyzed?
I'm not sure that I understand. Can you tell me a little bit more about what institutional menus are?
I think they're talking about maybe like a nursing home or a school feeding program where they don't actually have intake data, but they have menus, and it might be only for 2 menus, 2 days.
Oh, okay. I don't know. I think you would use it similarly, but we've actually just developed these methods for 24-hour recall data, which is a little bit different, I guess, than menu data. It's an interesting thought to try to apply it to something like that. Just off the top of my head, it seems like it would be possible to do it with 2 days. I would probably, I guess, select 2 or maybe a few more days kind of at random from the month if that was what you wanted to estimate. Yeah, but non-consecutive days also.
How important is the correlation between the random effects, and does this differ by dietary component?
It turns out to be really important. It can shift the estimate of the distribution if you don't account for the correlation, and it exists. In the EAT study, we looked at correlation between probability of consumption and amount consumed for the MyPyramid food groups. There were somewhere around 27, maybe 25 to 30 of these food groups, and we found that for about 80% of them that they exhibited this positive correlation between probability and amount. And we found that if we didn't account for it, then it would cause a problem in the estimation. So most foods have it. Not all do. I mentioned in the talk dark green vegetables don't tend to. People tend to consume about the same amount regardless of how often they eat it. And sometimes things like yogurt, let's say, which might come in standard size containers generally, like 6-ounce containers, it's going to be less likely to have that type of pattern as well. But we do see it in most foods, and actually it's also very common in other types of zero inflated data as well, not just dietary data, but physical activity and things like that also.
This goes back to the programs or the methods that you mentioned earlier. The question is whether these other methods have software that could be used to analyze episodically consumed components.
Which other methods?
In one of your slides, you talked about ISU method and a couple of others.
Oh, yes, okay. The ISU method, I think Kevin mentioned in the last webinar, does have software. It has a software called Seaside, which I have used to model episodically consumed foods. The seaside method, the only caveat is that it does not allow, if there is correlation between probability and amount, it'll print out a warning and say don't use this method because it assumes the two parts are independent. And I believe the multi-source method also has software available, and I'm not familiar with the software for the two other methods I mentioned.
Great, thank you. I think that covers all of the questions that we've received. Thanks very much for the time you took to answer all of those, and thank you for the excellent presentation, Dr. Tews. And to our participants, thank you for joining today's session. Next week in Webinar 4, we'll hear from Dr. Kevin Dodd about accounting for complex survey methods and estimating usual intake distributions. Thank you.
Thank you.